So in question 2, this is the setup that it's describing to you. So you've got these vertical parallel slits here, and the first thing it asks you is what you're going to see on this screen over here when this light is passed through the slit. So it's the usual thing, it's going to get diffracted by the slits. You're going to get superposition resulting in a pattern of constructive and destructive interference, and you get these fringes on the screen. So the important thing to get the marks here is that you've got to describe fully what you get. So because the slits are vertical and parallel, the fringes will be vertical and parallel. So you get vertical parallel fringes. The second thing is that because it tells you that's yellow, the light coming in, the fringes will be yellow, or the bright fringes will be yellow. And that's not too obvious to say, because obviously what you're establishing there is that the diffraction and interference doesn't change the wavelength, so the fact that the fringe is yellow, that's not really a trivial statement. So the fringes are yellow, and they're equally spaced. Okay, so they're equally spaced fringes, and the intensity is maximal in the middle, decreases to either side. So remember, if you actually looked at, measured, quantified the intensity of those fringes, you'd get something that sort of, you know, looked like that, if that was the intensity as a function of the position. Okay, so those are the features that you need to make sure you've described in part A. Part 2 wants to know, first of all, what the separation of the fringes will be. So the separation of the fringes is W is equal to lambda d over S. So lambda is 5.86 times 10 to the minus 7 meters. D is this distance, the distance between the sources and the screen, so that's 1.80. And S is the separation of the slits, so that's 0.36 millimeters, so that's 0.36 times 10 to the minus 3. So if you compute that, you get 0.00293 meters. Which is fine, and you could write that in millimeters if you wanted to, but you don't need to because it doesn't specify the units. But make sure you put a unit on there, not just a number. It also then wants to know the angle between the middle of the central fringe and the middle of the next but one, the second fringe from there. So it's easier to see that if we sort of look down on it from the top and say, right, here's our first centre of our first bright fringe there, and the second one is going to be over here somewhere, and then the third one is going to be, you know, over here somewhere. So we've got these equally spaced fringes here. So this distance, remember, is D, which is 1.80 meters, and this distance is W, which we've just calculated, is 0.00293 meters, or 2.93 times 10 to the minus 3 meters. And of course that's true for the separation, for all the separations, so that's also 2.93 times 10 to the minus 3 meters. So the angle that it's talking about is that angle, okay, which we'll call phi. Okay, and you can see how we can work it out, because if we know this distance and we know this distance and this is a right angle triangle, we can write down that the tangent of phi is equal to 2 times 2.93 times 10 to the minus 3, which is the opposite distance, divided by the adjacent distance, which is 1.80. Okay, so we can find that tangent, which gives us 0.187. And so the inverse tangent of 0.187 will therefore equal phi, which comes out to be which works out as 3.256 times 10 to the minus 3, and so phi is just the inverse tangent of that number, so it's tan to the minus 1 of 3.256 times 10 to the minus 3, which is 0.19 degrees. Okay, so very small angular separation between the between those fringes. Part 3 rather wants to know why, if we make these individual slits narrower, we see more fringes. So the key to this is the idea that the narrower the slit, the wider the angle over which the light is diffracted. So if you actually do the experiment with a single slit and you plot intensity as a function of angle, where this is 0, what you actually get is something that looks kind of like this. Okay, so you get most of the light in the middle, and then over this sort of range there's a significant amount of diffracted intensity, and outside of that there's not 0, but there are just these much smaller peaks. So most of the intensity is focused around the middle, but it turns out that this distance depends on the width of the slit, and basically the narrower the slit, the bigger that angular separation is. So if you get a narrower slit, it might look like sort of this, so that it's spread over a bigger range. Now, you don't need to know the detail of that, but you do need to know qualitatively that the narrower the slit, the wider the angle over which the light is diffracted. And of course that's important, because that means that the greater the extent of overlap, and therefore superposition, of the diffracted waves, and the more superposition you get, the more opportunities you have to get lines along which constructive interference occurs. So the more lines along which constructive interference occurs, which means that you get more bright fringes. So that's the idea. It's just, and you can sort of see that in a qualitative way by sort of imagining that if you have quite wide slits, you only get this sort of relatively narrow range of angles over which diffraction occurs. So you might sort of get this, and beyond that the intensity is really very limited. And so you can see that in this situation you're only going to get really quite limited overlap, like so. Okay, because along here there is just not sufficient intensity for overlap, so you're going to get quite limited overlap like that. Whereas if you have narrow slits, you get the intensity of the wave spread over a bigger angle, so you might get this. And now you can see that there's much more overlap occurring. Okay, just because of the bigger angular spread of the diffracted waves. So that's what you need to get. So that's the key idea. Narrow the slit, the wider the angle range, and explain the consequence of that is that you get more superposition. The broader that angular range and the more superposition you get, the more lines along which you get constructive interference, so the more bright fringes you'll observe. 2 part B then is a diffraction grating question. So we've got this kind of incident light coming in, and we've got a grating with 400 lines per millimetre, and it wants to know the angle between the straight through image, which is going to be directly in front, and then the one that's the first order, so the first image to either side of that one. So the relationship there that you use again is on your data sheet, which is that n lambda is equal to d sine theta, and theta is the angle that you want. So n is equal to the 1 for the first order image, and d is the separation of the slits or grooves or whatever you want to call them in the grating. And you get that just by saying, well, if there are 400 lines per millimetre, so you've got 400 lines per millimetre, means that you have 400,000 lines per metre, right? Because there's 1,000 millimetres in a metre, so 400,000 lines per metre. And that's equivalent to saying that the spacing is 1 over 400,000. Because if there are 400,000 of them in a metre, they must be spaced each 1/400,000th of a metre apart in order to fit them all in. So it's 1 over 400,000, which is 2.5 times 10 to the minus 6 metres is the spacing. Okay, so then we've got the number we need. So we get sine theta is equal to lambda over d, because n is equal to 1, which is 5.86 times 10 to the minus 7 divided by 2.5 times 10 to the minus 6, and that equals 0.2344. And so theta is the inverse sine of 0.2344, which is 13.6 degrees. Okay, so you're going to get 13.6 degree angle between that straight through image and the first image to either side of it. So you can see from this, if your 0 order image is coming straight through, your first order image is at an angle of 19 and odd degrees, you're going to get a second order image at 38 and odd degrees, and so on. But of course you can't keep going on like that, because in the end you're not going to, the maximum angle that you can theoretically diffract through is 90 degrees. Once you reach 90 degrees, you're in line with the grating, so you can't go any further than that. So in order to answer part 2 there, the highest order image, what you do is you set theta equal to 90 degrees. Okay, so then we have our equation, n lambda is equal to d sine theta, and sine theta is equal to 1 if theta is 90 degrees. So n lambda is equal to d if theta is 90 degrees. And therefore n is equal to d over lambda, which is equal to 2.5 times 10 to the minus 6. We worked that out in the previous part. That's the spacing of the individual grooves in the diffraction grating, divided by 5.86 times 10 to the minus 7, which comes out as 4.27. Now obviously n has to be a whole number. You only get a 0 order or a first order or a second order image, so the largest one you can actually get is 4, because what that's saying is that the 5th order one would be over here, which is impossible. So therefore the 4th order is the highest order image that would be visible. Is the answer to that question. So then in part C it wants to know why this diffraction grating experiment is a better way to measure the wavelength than a two-slit kind of setup. And there are really two issues there. The first is that the spacing between the individual grooves in the diffraction grating is generally much smaller than the separation of two slits in the two-slit setup. And remember that the separation of the bright fringes is W is equal to lambda d over S. So the smaller the separation, the smaller separation of the slits or the grooves in the diffraction grating, the bigger the separation of the fringes will be. And that's important because you've got to measure that, and obviously the bigger the separation of the fringes, when you measure it, the smaller the percentage uncertainty will be. You know, when you measure it with a ruler or whatever, the absolute uncertainty is always the resolution of the ruler, but the bigger that value you're measuring is, the smaller that uncertainty will be as a percentage. So that's the first thing, is that the maxima are more spread out. So the percentage error in measuring the distance between them is smaller for a diffraction grating. The second thing is that the effect of having many sources instead of just two is that you get much more effective destructive interference in between the maxima. And so you get much sharper, brighter lines than you would do with just two slits. And obviously that makes it easier to pinpoint the maxima. Again, you don't have to go into the detail of why that is, but you need to know that you get sharper, brighter lines from a diffraction grating. And that means that you can pinpoint the maximum more accurately.